Last class, we were talking of what we had called as vector valued functions, right? And we had seen that if I have a function f of one variable t that can be expressed as, if I'm able to write this as some component along the ith direction, another component of that same along the direction, and another component along the kth direction. Then such a function we had defined, we had seen that this is called as a vector valued functions. And then also seen, how to find the limits, how to check whether it is continuous or not, and so on and so forth. Similarly, I also said we can find the derivatives also. Now, since we know from our knowledge of calculus that if I have a Cartesian function y as some function x, then the derivative dy by dx that we know is nothing but, it defines nothing but the slope of the tangent to the curve. And especially when we find dy by dx at any point c, then it is nothing but the slope of the tangent to the curve y equal to fx at x equal. Okay, so that means whatever we want to study about the tangent can be studied with the help of derivatives. This we know from our knowledge of calculus also. Now, in case of vector valued functions, it becomes more important and useful because, especially when we are trying to find applications in physics, like for example, when you are studying, you all have studied planetary motions in physics. Okay, so basically, what happens is that, especially when you study things with regard to from the point of view of physicists, direction is important because there are so many things that that change their perspective, especially when it's the movement. So say movement of a particle, movement of a planet, movement of an object, whatever we want to study, whether it's going up, down, right, left, moving in an elliptical orbit. So things like that. So whenever we are interested in studying the movements, the direction plays an important role. And when we are talking in terms of movement, normally talk of, like, for example, we talk of displacement function, the position where it is at a particular moment. Then it moves with regard to some direction, with some rate of change of displacement with respect to time. Okay, and that we call as the velocity. So once we know the velocity, and we know very well that velocity is a vector function. Okay, and also if a particle is moving along a curve, then the velocity is always directed along the tangent to that curve. So if I'm interested in studying the velocity at this instant, then I'm interested in studying the tangent to that curve, that motion curve at that particular instant. That is why in such situations, directions and vectors play a very important role. And that is why when we are talking of vector valued functions, to find the tangent vector, it's important because tangent vector is going to define. See, if you go back to the very first classes when we talked of the graphing, right? We just observed how the derivative changes. If the derivative is positive, we know that the function is moving in an increasing direction. If the derivative is negative, we know that it is moving in a decreasing direction. But when we are talking of vector functions, the tangent vector defines the direction of motion. Like if the tangent is moving from here to here to here, that means this is how your curve is moving. Okay. So the tangent vectors play an important role while defining the motion of particles. So that is why when we specifically study tangent vectors for vector valued functions as well. Okay. Now, before we go on, obviously, we know that tangent is nothing but derivative, and we have also seen in the last class that if my f is a vector valued function, then and I have to talk of df by dt, then this is nothing going to be, this is nothing else but the derivative of the first component with respect to t, derivative of the second component with respect to t, and the derivative of the third component with respect to t. This is how the derivatives are going to behave. Okay. Now the thing is that if I am saying I am interested in finding the tangent vector, that means what? That means I am interested in finding that line which serves as the tangent line. Okay. So if I say tangent vector, that means I have two things attached to it. Number one, I have to find the equation of the line also. And number two, I have to find the direction also. In which direction is that line inclined? In which direction is that line going? So that only is going to define my tangent vector. Okay. Now derivatives we have also seen are nothing but like if I say a derivative, it is a function in itself. But when I say a tangent vector, that means we are computing it at a specific point. Now, at a specific point, when we are talking of motions here, a specific point would mean an instant. Why? Because it is varying over time. Okay, so that means I might be interested in finding the tangent vector at when t is say specifically t naught or t1 or something like that. Okay, so normally like even in physics when you have studied, when we study motions, we we say okay, when the motion starts it is t equal to 0. Okay, after a certain stage it is t equal to t1. So after a certain stage a particle has moved from position A to position B, right? But in between a lot has happened, right? So to study how that lot has happened or how that particle has actually moved from its position A to position B, we are interested in finding the tangent vectors. Okay, now now, since we are now studying vectors with regard to both all the three components I, j, and k, so now we'll bring in some knowledge of three-dimensional geometry that we have studied. Now, if you go to class, then you must have defined something as right line, okay, which is nothing but a straight line, right? How do you find the equation of a right line? इसको ऐसे लिखते हैं ना, x, supposing you are finding we are interested in finding a right line that passes through the point say x naught, y naught, z naught. Okay, and of course there are specific parameters that define a particular characteristic of the straight line, and we define it as x minus x naught upon say a is equal to y minus y naught upon b is equal to z minus z naught upon a. Is that right? Now, A, B, and C, you know what they are. So I'm not going to repeat. Okay. So in a way, to write down the equation of a line, says इसको हम क्या लिखते हैं? Equal to t करते हैं या you can call it as lambda also. Then how do you define the line? As x naught plus a lambda, y equal to y naught plus c lambda, and z equal to z naught plus c lambda. This is how a straight line can be represented. Am I right or wrong? ये तो सबको याद है ना?
Yes, ma'am.
This you have already studied, right? So that means either if I write it in this form or if I write it in this, both of them are going to represent a line, right? But then to have a line in this form, what do I need? This thing. What is this? This is the point through which the line passes, right? And I need this also. Then only I'll be able to find the straight line, right? So what we do is to find a tangent vector, like say supposing चलो हम ले लेते हैं, तो इसमें example है. Let's take this. I am interested in finding a tangent vector. This is example number 3. I'm interested in finding a tangent vector at a point P naught where t is equal to 0.2. Okay, so that means this 0.2 is going to serve as your t naught. Okay, the graph of a function which is defined as ft equal to e to the power 2ti plus t squared minus tj plus log tk. Okay, now see, this is the motion. Okay, I mean, that means this is how that particle is moving, in the sense that along the x-axis, the motion is being governed by this function. Along the y-axis, it is being governed by this function, and along the z-axis, it is being governed by this. Okay, so that is why this becomes the component of this f along the positive direction of x-axis, because I have a plus I here, right? Similarly, this is the component along the y-axis, and this is the component along the z-axis. This is how it is going to be defined. Now, when we are saying at a point P naught, okay, so that means the point is going to be some point on, let's say, it could be any motion, like, I don't know how the graph is, but it could be something like this. Okay, this is moving. In this direction, it is moving. So this is when t is 0, and this is when t is, say, t1. But in between somewhere, some t has happened when t is 0.2. ये एक specific point हो गया. So when t is something else, I'll get some another specific point. So that means at one specific time of t, if I am interested in point, then these components are going to give me the position vector, right? See, that means in a way, this is your xt, this is yt, this is your zt. This is how your graph is moving, your particle is moving, and your equation of motion is being governed. Okay, so if I'm interested in finding a specific point on the curve, then like that means my x naught is going to be x when t is t naught, right? Similarly, my y naught is going to be the value of y when t is t naught, and my z naught is going to be the value of z component when t is t naught. Okay, so basically this is nothing but e to the power 2t when t is 0.2, because this is the specific point on which I have to find the things. Okay, similarly, y naught is going to be t square minus t when t is 0.2, and z naught is going to be log t when t is 0.2. So they'll be my specific points. I can find values, not a big deal. Okay, this will give me my x naught, y naughts, and z naughts. Finally, to write down the equation of the tangent vector, I need a, b's, and c's also, or the corresponding l and n's, whatever you want to call them. I'd rather call them a, b, and c. Okay. Now, to find those a, b, and c, now since they're going to be the corresponding things for the tangent vector, and tangent comes somewhere from the derivatives. So what we'll have to do is find f dash t. Okay, and what will be that? That will be nothing but dx dti plus dy by dtj plus dz by dtk. Right. And what was your x? Your x was e to the power 2t. Okay. So that means it's be d by dt of e to the power 2ti plus d by dt of t square minus tj plus d by dt of log tk. Okay, so that means what? This is nothing but 2 e to the power 2ti plus 2t minus 1j plus 1 by tk. This is your f dash t, right? These components of f dash t at t equal to 0.2, which is your t naught, they are going to give you your A, B, and C. Okay, so basically that means the value of my that I need to find is going to be nothing but 2 e to the power 2t when t is 0.2. Similarly, your B will be 2t minus 1 when t is 0.2, and your C will be 1 by t when t is 0.2. So you will have this as the values. You can compute them. Okay. So once you have them, Then you can write the equation of the tangent vector also. So your tangent vector will be given by x naught plus a. I'm so used to calling it t, but चलो कोई नहीं. Y naught plus b lambda and z is equal to z naught plus c lambda. Or you can write it as x is equal to x naught plus at, y is equal to y naught plus bt. I mean, it's understood that t is a parameter here. Okay, and then this together will give you the equation of tangent vector. Is this clear? Hmm?
Yes, ma'am.
This is how we find the tangent vector. Now, one more thing that we need to define here is that in case for a given function, for a given vector valued function ft, this is given as I find f dash t. Observe that, I mean, of course, t belongs to some interval I, say let it be some t1 to t2, could be anything, could be from 0 to infinity or from some specific values. And we observe that f dash t, the derivative of this vector valued function, is continuous for every t in this interval. Okay, that means every point of this interval, the derivative of this vector valued function is continuous, and f dash t is not equal to 0. Okay, it does not, the derivative does not vanish. Okay, and the derivative is continuous, then the curve f is said to be a smooth curve. Okay, so that means the smoothness in case valued functions is going to come. See, in case of Cartesian functions, what did we observe? That the curve is smooth if the derivative exists, right? And we had seen the difference between mod x and the parabola and things like that, right? But now we are saying that the same carrying over, because each component now itself is of a function. Okay, so that means together they will become smooth provided the derivative is continuous, it does not break anywhere, and the derivative does not vanish anywhere. Then the curve is said to be smooth. Okay, so but what happens is, the obvious question is, what will happen to such curves? Can we not study those curves that are not smooth? And we say, no, no, no. Of course we can, because mathematicians are clever. So what we do is, okay, let's not talk of smooth in the whole interval. Supposing my interval is t1 to t2, right? Now it could be that from, say, supposing somewhere here is t1, somewhere here is t2. It could be that from this position to some t not here, it is continuous, the derivative is continuous and does not vanish. But say supposing at t naught the derivative vanishes. So if the derivative vanishes at a particular point, so we'll end up saying that no, the curve is not smooth in the whole interval I, if I go by this definition. Okay. So we say, okay, let's split this interval. Instead of studying for whole t1 to t2, I'll study for t1 to t naught first, and then from t naught to t2. यहाँ पे तो continuous है, यहाँ पे भी continuous है. So what is happening? The curve is piecewise smooth. That means if we take small, if we consider the curves in pieces, it is smooth. So that each piece, whatever we wish to study for smooth curves, can be now done piecewise. Maybe not as a whole, but yes, piecewise we can do it. And this piecewise continuity, piecewise smoothness, you will appreciate when you study real analysis in details or study multivariate calculus. You get to know that, see, instead of saying कि हम इस function को study ही नहीं करते, it's better to say let's study it in pieces and then combine together the pieces. जहाँ कुछ नहीं हो रहा उसको हम उस पे हम उसको study ही नहीं करेंगे. Okay, so this is how smoothness and piecewise smoothness of curves is defined. Then, of course, the derivative, the property which the derivatives of vector functions satisfy are exactly similar to the derivatives of Cartesian functions or the analytic functions that we have studied. We can talk of higher order derivatives also for the vector value functions. If I can find the first derivative, I can find the second derivative also. That means we can differentiate a given function any number of times we want, provided the derivatives exist. So we can, that means for a given f, I can find f dash, I can find f double dash, and so on so forth, provided the derivatives exist. They might be zero, but then definitely. Then all the properties, say supposing f and g are two vector valued functions, then the derivative of f plus g is going to be the derivative of f plus the derivative of g. Okay. Similarly, uh, the product rule applies that dot d, g dash, you know, if you're trying to find this, then the product rule applies. The derivative of first dot the derivative of second plus the first dot the derivative of second. Okay. Similarly, you can have the cross product rule as well. If I have to find the derivative of the cross product, okay, so it's going to be f dash cross g t plus f cross g dash t. Okay, so all those product rules, chain rule even, they apply for vector valued functions. They get applicable here. Okay, and I think you can verify if you do this exercise. You just have to verify these properties for the given vector valued functions. Okay. Similarly, we can talk of the integrals also. Okay, of a vector valued function. So if I have ft as a vector valued function defined as f1ti plus f2tj plus f3tk, then the integral of f dt is nothing but integral of f1t dti plus integral of f2t dtj plus integral of f3t dtk. Okay. Now this becomes helpful, when we do problems related to velocities and accelerations. Okay. See, again, now I'll just go back to a little bit of physics here. Your V is nothing but dr by dt. Okay? The rate of change displacement, where r as a function of t is your displacement function. Okay. Then rate of change of displacement with respect to time is the velocity. And we observe that modulus, in fact, in vector valued functions, now we don't say modulus, we say norm. Okay, so इस तरह से लिखते हैं. So this is actually the magnitude, the scalar part of the velocity, which we have been calling as speed. यही बोलते हैं ना इसको. So basically that means v upon norm v or mod v, जो तुम बोलते हो, ठीक है? This defines what? This is what? A unit vector. Any vector upon its magnitude is nothing but a unit vector. A unit vector means what? Unit vector means a vector whose magnitude is 1 and has a direction attached to it. Okay. So if I just talk of this quantity, v upon mod v, norm v or mod v, then this defines the direction of velocity only, because the magnitude of this unit vector is 1. Okay. So why I'm saying all this is because, it could be that in the problems, in the exercise problems, we might be using it. Okay. Now, okay, let's see the relationship between these three vectors. We'll be dealing mainly with these three only. Say, supposing I say my r is your displacement function, which is nothing but f1ti plus f2tj plus f3tk. Okay. Then v, velocity, nothing but d by dt, which is actually nothing but f1 dash ti, the derivative of the first component, plus f2 dash tj plus f3 dash tk, right? And acceleration is what? The rate of change of velocity with respect. So that means acceleration is actually nothing but the second derivative of the displacement function, right? Because once we differentiate the displacement, we get velocity. We differentiate it again, we are getting acceleration. So basically, this is nothing but one double dash ti plus f2 dash tj plus f3 double dash tk. Right, so this is going to be your acceleration vector. So that means if I am given the displacement vector or the displacement function, I can find the velocity and the acceleration by differentiating that depending upon how many times we are doing it. And not just this, if I have to find the velocity at a particular instant, that means could be that I'm given some r and I'm asked to find the velocity when, say, t is some specific t naught. So that is also not a big deal. I just have to find the velocity and then find it when t is t naught, right? So this is when we are differentiating, right? But the problem could be the other way around also, in the sense that it could be that for a particular motion or for a particle, I'm given the velocity with which it is moving, okay? And I'm asked to find its displacement vector or the position vector, okay? So if I'm given v, then to find r, what do I have to do? I have to integrate, because it's like we have to move back, right? You differentiate r to get v. So अगर यहाँ आना है, तो what did we do? We differentiate. But supposing I have from here to here, that means I have to integrate. I have to perform the inverse operation of differentiation. But when we integrate, I mean, it's not a definite integral that we are finding. It will be a general integral. So if it's a general integral, that means it will have a constant of integration also attached to it. Okay. So that means if I have to find v, if I have to find r using v, then it's going to be integral of this, which will be nothing but then something like this plus some constant c. Now, mind you, now this constant is not just a scalar, because where we are talking of vector functions. So that means the constant of integration that we are going to bring in will also be a vector like this, C1i plus C2j plus C3k. Right? So that means in general, when we find the integrals, the constant of integration also is a vector quantity. Okay. Now, the point is that as far as this C1, C2, C3 are left as C1, C2, C3, that's a general integral. But I might be given, I might be in a situation where I have to find the displacement vector when the velocity vector is given to me, but that too at a specific instant. When? Maybe the beginning, maybe the end, and so on and so forth. Okay, so to find those constants of integrations, we need conditions that we call as the initial conditions. Okay, so what we do is, once we have integrated and obtained a general integral with the constant of integration involved in it, we use the initial conditions. These initial conditions will help us to find the values of C1, C2, and C3. So once you are able to find these values, you can substitute here and then you get the answer for that. But mind you,
C2, C3 are called initial conditions.
No, the C1 to C3 are the general constants. The conditions under which we will find C1, C2, C3, they are the initial conditions. Okay? That could be the situation. Like, for example, let me do something. Yeah, like it says the velocity of a particle moving in space is Just look at this question number, say 31. I mean, again, I have an older edition, doesn't matter, forget about the number. I'm just giving you, I'm taking an exercise problem now, okay?
Ma'am, your voice is breaking.
See,
Yes, ma'am, from initial condition.
breaking is an internet issue. I'll repeat, okay? Um, as I was saying, the initial, um, if the constant C1, C2, C3, the values of these C1, C2, C3, the conditions under which we have to find the values of C1, C2, C3 are called as the conditions. Like for example, I have a particle moving in space whose velocity is given by t square I minus e to the power 2tj plus root tk. Okay, this is the velocity with which that particle is moving. Now I have to find the position vector for this particle. That I have to find RT. Okay, and RT as such is nothing but VT dt. Okay, now this will be what? Now, as far as my knowledge of vectors is concerned, it will be the integral of the first component minus integral of second component plus integral of the third component. Is that right? So I can write that. Now what is the integral of t square? T cube by 3, right? What is the integral of e to the power 2t?
2
Yes, integral of t.
2 by 3 t to the power 3 by 2.
2 by 3 t to the power 3 by 2 k. But since I have integrated now, I have a constant of integration also attached to it, which is a vector. It is not a scalar now. Okay. This is a general integral. Or if you want, you can write it as t cube by 3i minus e to the power 2t by 2j plus 2 3 t to the power 3 by 2k plus I can write this c1i plus c2j plus c3k because it's a vector. So it has some components, maybe some of them are zero, that is immaterial. Okay, we'll find the value. Now, this is a general displacement function. That means any particle with this as displacement vector will have this as the velocity function, right? Because if you differentiate this function, you are going to get this. Okay, but I'm not interested in finding all such particles, all such motions of particles. I am interested in finding that motion or that for that particular particle for which r at 0 is I plus 4j minus k. Now, what does this mean? That means at t equal to 0, this should be the displacement function. That means now we have a specific particle. That means it's like we have this family. Okay, the integral that we have got is a family. All those particles which are moving with this as the displacement function will have this velocity, right? But I'm saying no, I'm not interested in finding the whole family members. I'm interested in one particular member. Kaun which one? The one that for which at t equal to 0, this is your displacement function. Okay, so this is your initial condition. That this is how it is given. Now we'll use this initial condition to find the values of C1, C2, and C3 because this is your RT which you have obtained. But we have to now use that. We have to find C2, C3 such that r at t equal to 0 is given by this function. Okay, so what we do is we simply put at t equal to 0 what should be the left hand side? I plus 4j minus k. This is what we want, right? And what will happen from here? Just put t equal to 0 right hand side. What will happen? The first component at t equal to 0 is 0i, right? At t equal to 0 is minus 1 by 2j. At t equal to 0 is plus 0k plus,
Ma'am, R0 is given.
फिर से बोलो बेटा.
R0 R0 is given.
Yes, it is given.
Oh,
What I am saying,
okay.
initial condition will always be given. Then only we can find the values. Otherwise, we have to leave it as a general function. Okay? Plus,
Yes, ma'am.
plus C3k. Okay. Now you can combine the components of I, j and k. Compare them. When are two vectors equal? When their respective components are equal. Okay. So if you compare, अब यहाँ पे right hand side क्या बन गई? C1 plus 0, which is nothing but C1. Then it's C2 minus 1 by 2j, right? Plus C3k. Now, if you compare them with the left hand side, now you have these two vectors equal. So basically, when you compare the values, you get C1 as 1, right? C2 minus 1 by 2 equal to 4, C3 equal to minus 1. You have now all the values of these unknown constants with you, which can be now substituted back here. So that becomes a particular particle's displacement function. You change the initial condition, your displacement function will change. Okay, so that means to find the displacement function from velocity, initial conditions must be given to us. Then only we can find them. Okay, and not just this, depending on how many times are we integrating, so many initial conditions are required, you know. Like इसमें तो हमें velocity दिया हुआ था, हमने displacement निकाला. It could be कि मुझे acceleration दिया हो, right? Like my A could be given as A1i plus A2 plus A3k. Now I have to find R. So from A, we'll have to first find V, which is nothing but integral of the acceleration. Okay, so when you integrate this, it will have some constant vector, some c, right? But we are not to find c. So again, that means what? Now we will use the initial conditions given for velocity to find this c. Okay, but now if I have obtained v, I can.
Ma'am,
Hanji.
ma'am, integration of acceleration, you have explained that it is jerk.
क्या इंटीग्रेशन ऑफ एक्सेलरेशन क्या फिर से बोलो किसने भी क्या
Ma'am, is jerk. Ma'am,
better write it in the chat box, your voice is breaking. इंटीग्रेशन ऑफ एक्सेलरेशन वेलोसिटी तो होगा, रेट ऑफ चेंज ऑफ वेलोसिटी इज एक्सेलरेशन, तो उससे उल्टा नहीं चलोगे.
yes, ma'am.
ठीक है. So you have this. Now that means we need initial conditions on velocity to find this constant. So once we have obtained the velocity function, then we again integrate it to get the displacement function. Like for example, say supposing you are given A as, you are given the acceleration function as, say, it's given as t square I minus 2tj plus e to the power 3tk. Okay, and you are given two conditions. R at 0 is 2y plus j minus k, and v at 0 is I minus j minus. Okay, so that means we need as many conditions as we have the constants of integrations. So if we are integrating only once, we need one condition. If we are integrating twice, we need two conditions. Okay, Similarly, your v, that means now your vt will be nothing but integral of t square minus 2 integral root t plus j plus e to the power 3t integral dtk. Okay, and plus you get some constant c here. How will you find this c? By using this condition, because this is the condition on the velocity. Okay, so then you will get some value here the way we done up in the previous problem. Now you integrate it again and you will get your RT. Is that it? Hmm? Is this fine?
Yes, ma'am.
There's one result here which is important. I'll just explain what it is all about. It's given as a theorem, so it is important. Now, see, this theorem, it's called the orthogonality of a function of constant length and its derivative. Now, what this theorem basically says is that if you have a non-zero vector function ft, okay, that means the function does not vanish. Okay, the function is non-zero. Function is such that it is differentiable, okay, and has a constant length. Okay, function is differentiable and has a constant length. Then the result says that then f is orthogonal. Orthogonal का मतलब क्या होगा? Perpendicular, है ना? So instead of saying vectors are perpendicular, we say vectors are orthogonal to each other. So f is orthogonal to the derivative vector. F dash t. Now this property could be used in some of the exercise problems, where you use this. So, but the only condition is that my function should be a non-zero vector function. That means the function does not vanish in its own. It's differentiable and has a constant length. Okay, so that means magnitude of this vector is constant. It has a constant length. Okay, so it is constant. Then we have to prove that f is orthogonal to its derivative. Orthogonal कब होगा? When the dot product of the function and its derivative is zero. तभी कहेंगे ना इसको orthogonal.
Yes.
This is what we have to prove here. Okay. Now let's say, okay, let's see why this is too simple. That's why I'm doing it, but it's too simple. You can do it on your own also. I say let ft be a non-zero differentiable function. We want, now since we want the length to be constant, I say let mod of ft, the magnitude of ft be r, some scalar quantity r where r is constant. Let me write it here. R where r is constant. Okay. Then see, if you just look at here, what will be r square? Right, square will be nothing but mod of ft square, which I can write as ft dot ft. ये तो result है ना हमारे पास. A dot A is mod A square. Vector की property है.
Yes, ma'am.
Okay. So I say r square is ft square, which I write as. So now what I'll do is, instead of writing t again and again, understood, I can write it as f dot n. Is that okay? Now I say, okay, let's differentiate both the sides with respect to t. Both the sides with respect to t. Okay. Now see, your left hand side is what? R square. And what was r? A constant. That means the derivative of r is constant.
0.
Left hand side will be 0. And your right hand side will be what? F dot f dash, because f is a function of t. So it will be the derivative of the dot product. And just a few minutes back, I explained that the derivative of dot product is going to be derivative of the first dot second plus the first dot the derivative of the second function, because it follows the product rule of derivatives. The vector functions follow the product rules of derivatives, right? Which is nothing but twice dot f dash. I can take that. And what is this equal to? 0. So that means f dot f dash is 0. So the two are orthogonal to each other. Is that okay?
Yes, ma'am.
This result, you might be needing it in the next article or in the exercise. Just let you know when do we need it. But then this is a major breakthrough, that we use this result a lot for vector value functions. So basically, this finishes off your 10.2 as such. Okay.